see how we can calculate the coefficient of restitution when you allow one surface to fall on another surface and rebound. Just the example I showed you. Now consider a ball dropped from a height h1. Alright, this is the floor. A ball is now going to be dropped from that height h1. Now look at that. The ball is dropped from a height h1. Now its initial velocity is 0, its acceleration is negative g, and it falls through, its displacement is y equal to negative h1 because it is downward displacement. Now if v1 is the velocity of approach to the floor, you see, when you drop an object, just before it hits the floor, it will have a velocity. Is that right? That's the maximum velocity. If v1 is that velocity, then we have, that is the velocity with which the ball hits the floor. Then that v1 squared will be equal to v0 squared plus 2ay. Now, v0 is 0. A is negative g, is that right? And y is negative h1. Let's replace that. Therefore, v1 squared equal to 2 times negative g times negative h1. Negative g times negative h1 becomes positive gh1. So, if v1 squared equal to 2gh1, then v equal to square root of 2gh1. If the ball rebounds, if the ball now rebounds with a velocity v2 to reach a height h2, can you write a similar equation for the rebounding process? So the ball has now rebounded. Let's look at that again. After the ball hit the floor, it rebounds, and the velocity of rebound is v2, so that its initial velocity here now is v2, final velocity is 0, is that right? And the displacement y equal to positive h2. So in a similar way, I can show that v2 equal to square root of 2gh2. Okay. So, when a ball is dropped, when I drop a ball, suppose this is the floor, the dropped ball will reach the floor with a velocity v1 equal to square root of 2gh1, and it rebounds to a height of h2. The velocity of rebound will be square root 2gh2. Alright. Since the floor is at rest, remember the collision is between the ball and the floor is at rest. v1 is the velocity of approach and v2 is the velocity of recession, isn't it? Since the floor is at rest, the velocity of recession, well, the velocity of approach is v2i minus v1i. And v1i is the velocity with which the ball hits the floor. v2i is 0. Therefore, the velocity of approach simply is v1, the velocity that the ball acquires as it hits the ground. And the velocity of recession is v2. So here we have velocity of approach and velocity of recession right there. And we can use that to calculate the coefficient of restitution. So E equal to V2F minus V1F divided by negative V2I minus V1. That means velocity of recession divided by the velocity of approach. Velocity of recession is V2 and the velocity of approach is V1. Therefore, that is square root 2gh2 divided by square root 2gh1. and that will be square root of H2 over H1. A very simple way to calculate coefficient of restitution between two surfaces. If from a height H1, and after hitting the floor, if it rebounds to a height H2, then the coefficient of restitution between the object and the floor will be square root of H2 over H1. Let's do a calculation of E. Let's calculate the coefficient of restitution between this ball and this steel surface. What all I need to do is, you can see this is graduated. This height is 50 centimeter. So I'm going to drop it from a height of 50 centimeter. My H1 is 50 centimeter. Let me write that. H1 is 50 centimeter. And what all I need to do is measure H2. It rebounded up to 44. So your H2 is 44 centimeter. Therefore, E equal to square root of H2 divided by H1. That will be square root of 44 divided by 50. You don't need to convert the unit because of the ratio. I'm going to leave it for you to calculate that. Let's find the coefficient of restitution between two other surfaces. This is a lead ball. Alright, I'm going to drop it from a height of 50 centimeter. See how much it rebounds. Well, did you get to see how much it rebounded? Well, try it again. Well, it rebounded up to about 5 centimeter. You can see the collision is almost perfectly inelastic. So in this case, the coefficient of restitution is square root of 5 divided by 50. It's a very small value. So this arrangement can be used to find the coefficient of restitution between this surface and any other surface, if you can drop it onto there and measure the height to which it rebounds. We will now do this problem. A dropped ball bounces to 60% of its original height. What fraction of its mechanical energy is lost each time it bounces? What is the coefficient of restitution of the floor ball system? Well, H2 equal to 0.6 H1. That is what this means. It rebounds to 60% of the original height. The final height, the height of rebound, is 60% of the original height. The initial potential energy of the ball, U1, is mgh1. When it rebounds to a height H2, its potential energy U2 is mgh2. And replace that H2 by 0.6 H1. So the potential energy when it rebounds, or the final potential energy, will be 0.6 mgh1. 0.6 mgh1. But mgh1 is the initial potential energy. Therefore, the final potential energy U2 is 0.6 U1. Is that right? Okay. What is the energy lost? Is U1 minus U2. mgh1 minus 0.6 mgh1. U1 is mgh1. U2 is 0.6 mgh1. And therefore, the energy lost is 0.4 mgh1. We want to find the fraction of the energy lost. What is the fraction of the energy lost? The fraction of the energy lost is the energy lost divided by the total energy. If we say 10 students in this class are absent today, and if you ask me what fraction of the whole class is absent, it will be 10 divided by the total number of students. So the fraction of energy lost is the lost energy divided by the original energy. So that will be U1 minus U2 divided by U1. Now U1 minus U2 is 0.4 mgh1 and the original energy is mgh1. Therefore the fraction of the energy lost is 0.4. If I ask you what is the percentage of energy lost, well, 0.4 is 40%. Okay, now E equal to square root of H2 over H1. You can do that right away here. H2 is 0.6 H1, and so that will be square root of 0.6 H1 divided by H1. H1 and H1 cancels. Therefore, E equal to square root of 0.6, that is 0.7